Hi, everyone, and welcome to this impromptu stream. Or if you're a normal student in my class, probably you're just watching this on YouTube. I'm sorry, something has come up on Monday, so I can't actually teach class during the normal time. So I am pre-recording this lecture. So if you are here on Twitch, hello, right now. Yeah, this is totally unscheduled, but hi, anyone on Twitch. If you're on Twitch, you can follow along. Otherwise, you'll have to lob me any questions in the office hours later this week. So today's topic, fortunately, is going to be kind of a rehash of last lecture, but we're going to do it in a very specific context. Specifically, we want to talk about the so-called metacircular evaluator. Now, what do I mean by a metacircular evaluator? So the term metacircular evaluator was popularized by structure and interpretation of computer programs, and the basic concept is implementing an interpreter for a language inside the interpreter itself. So that's where the circular in the name comes from. You're sort of, for example, using JavaScript to implement JavaScript, or you're implementing Scheme to implement Scheme. That's how it was done in SICP. And by doing it this way, it is a very interesting way of thinking about how programming languages are put together, because ordinarily if you wanted to write an interpreter from scratch, there is a lot of things that you have to implement, right? Like, just imagine your basic programming language with mathematical operations. Well, you need some sort of library to actually implement these mathematical operations. And typically, any real world language is going to be implemented inside C or some other similarly low level language. And as a result, there's actually a lot of stuff you have to do to get going with an interpreter. But in a metacircular evaluator, well, you've got your host language, so most of the things you don't care about, you can simply defer to the host programming language to provide for you. Need addition in your JavaScript interpreter? Well, no problem. Just use the addition in the parent interpreter. And if you are looking for to actually like play around with some particular concept in the language, that's when you'll go ahead and redo it inside your implementation. So there's another sense in which the metacircular evaluator is circular, and that's the sort of very primary evaluation loop, namely between eval and apply. And we'll see more what I mean by this as we get into the code here. But the homework this week is to essentially implement an interpreter for JavaScript in JavaScript. This is the Metacircular lab, and what this lecture basically is we're going to do it on the whiteboard, pencil and paper style. And if you so please, you can probably copy the stuff I write on this whiteboard lecture into your homework and get it working. But, I also encourage you to try it by yourself. All right, so that's all for intro. So let's get started with the actual implementation. So before I can get started implementing our metacircular evaluator, I have to set the stage by talking a little bit about what I mean by, what data structures I'm planning to use here. And so there's two data structures that are important. So one is the abstract syntax tree, and the other is the runtime environments. So we'll go ahead and do these in reverse order. So here is a simple JavaScript program. So let's suppose we have x equals 0, then var f1 equals, let's say it's a function, and it's going to be var x equals 1 on the inside, and then we'll define another nested function. And then we're going to return x. And then we're going to, inside that function, we'll return x. Basically, the intent being that, hey, this x is referring to the x in the enclosing function. And they'll go ahead and immediately call f and return it. And then let's, return f1 equal to 1 basically saying whether or not we actually implemented this correctly, and we get 1 as the return value for this function and not 0. So what we will be interested in is the state of the environments at a certain point, specifically here where we want to check scope. So let's take a look at what this function's scope environments look like at this point in time. So we've obviously got a top level environment, and it's got a binding for x, which is set to 0, and it's binding for f1, which points to our double bubble, as we said before. The double bubble points to some code, so I'm going to have to give names for these functions. So let's name this function impl f1, and let's name this function impl f2. So we've got our function, and one of these is going to, so the environment for this function is going to point back to this environment, and the code pointer for it is going to point to impl f1. And I think that's it for this environment, right? So when we called f1, that caused a new frame to get created. So we'll go ahead and create this frame. This new frame has 2 new bindings in it. It's got x, it's got f2, and we've got an access link going from let me do this the same way I did it in lecture. We've got an access link going to the same place that the environment pointed to. X is 1, f2 points to another function, another closure. The implementation is impl f2, and the environment is simply where it was defined. And then finally, when I call f2, that creates one last scope, which in this case is empty. And where does its access pointer point to? Well, it just points to wherever the function's pointer was. And now we can see that if we were to go ahead and evaluate this return x, we'll go ahead, look for it here. It's not there, so we'll go and follow the environment, the access link, and then going to the parent environment, and then we'll finally see the value that we're looking for, right? Okay, so this is the pencil and paper thing that I put you here. So we're actually going to implement this in JavaScript, and if I'm going to implement this in JavaScript, I to represent this. And JavaScript is full of objects, and so we're just going to use objects to represent this situation. So I need to give some names to all of these environments. So let's call this S0, let's call this S1, and let's call this S2. They're in reverse order for no. I mixed the order up. Hang on. Let's call this S0. Let's call this S1. Let's call this S2. So I've given names to all of these things, and so I just need to define variables. What I'm going to do is I'm going to define an object. We're going to represent these as objects, right? So these objects will have some fields. They'll have values on the fields, and we're going to represent this as basically a object with 2 fields. One field saying what the code is, and then that'll be just some string like impl f1 or impl f2, and then it'll have an environment pointing to the object in question for each of these environments. So if we were to ask ourselves, hey, what does this look like in code, I'd probably say something like, we'll define S0 to be an environment. For now, I'm not going to put anything in this environment. I'm just going to assign things to it later. You'll see why in a moment. And so it has a few fields. So it'll have a field for X, which I'll set to 0. And it'll also have a field for F, which I am going to allocate a closure for. And so remember that I said the format for closures was going to be, I'll have a code field and an environment field. So the code in this example, well, I need a way to refer to the code. So I'm just going to call it impl f1, which is what I named the function in this particular case. And what is the environment going to be? Well, we said the environment was going to be that environment, so I'm going to refer to S0. So that's why I had to pre-declare S0 so that I actually, could refer to it. Okay, so I'm just going to go ahead and do S1. So when I do S1, this time I need to give it a parent. So I'm going to just give a special field called __ parent for this particular case, and I'm going to set it to S0. Technically, this doesn't work if you define an identifier named parent, but whatever, we're just going to roll with it. And it's got two fields, X and F2. And once again, F2 is a closure, so I'm going to, have a code pointer for it. And I'm going to give it an environment, and the environment's just going to be S1, which once again is what I allocate the closure in. And finally, I have to define an S2, and this is just going to have a parent pointer and no environment, no fields in the environment. We're just going to represent all of these as objects. We'll use object fields as saying what is stored in the environments. We'll have a magic field named parent, saying what the parent environment is, and then we will have functions will be represented as objects with two fields. So now what we're going to do is we're going to write some code to actually operate on the representations we have discussed just now. A good place to start is with a variable lookup, which we just looked at how it was actually done on the environment we had in this situation. So let's go ahead and try writing this function. So we're going to write a function, lookup variable value, and we're going to take some arguments. So we need to take up the identifier, which is just a string saying what the variable we're going to look up is. And we need an environment, which just says, what environment are we actually going to start looking for this variable in? And how are we going to go about implementing this? Well, if the identifier is in the environment, then we are just going to go ahead and return that value as per the environment. Nothing else to do in this situation. Now let's consider the next situation, which is that it's not in this environment. Well, maybe the environment has a parent pointer. It has an access link pointing to the next environment. So if the environment contains one of these __ parent fields that we were using to represent access links, then what we want to do is we want to recursively look up into the parent environment to see if we can find the variable there. And finally, if there is nothing else to do, then we'll just throw an exception saying that we can't find the variable in question. So that's it for implementing lookup variable value. We can see that it's very simple. We just followed exactly what our plain English description was from the previous lecture, and we were able to write down all the steps for it. And most of the other implementations are going to follow similarly. So another thing you might reasonably want to do is set variable value, which instead of just looking up a variable, also sets its value in the program. But when we set a variable in JavaScript, it's always valid to set a variable in JavaScript. And so if there isn't any binding anywhere, what JavaScript will do is it'll just go ahead and bind it in the very top environment. So let me save this. Nope, not that. I want to save here. And then we will just go ahead and delete this code. So let's try and implement setting the variable value. So once again, I want to say, let's try to set a variable value. So pretty similar to lookup, but this time we'll also have a value that we want to set. And there's a few ways we can go about doing this, but we can also do this one recursively. So we will say if id inenv then we'll just go ahead and set it and we're done. Otherwise, if the parent is here, then we'll go ahead and try to set it in the parent environment. And now, unlike that, if it's not in this environment and there's no parent environment, meaning that, there's nothing, there's no more environments to go, we'll just go ahead and set it anyway. Yay. And that's how you set variable value entirely in code using the data structures that we have here. All right, so let's go ahead and take a look at the runtime environment. Sorry, not the runtime environment. Let's take a look at the AST. So I am going to delete all of this. Let's look at the AST. So if we're going to write an interpreter for JavaScript, we need a way to actually talk about syntax trees in JavaScript. And so in the lab, we're using a little parser for JavaScript called Acorn, which gives us the following syntax tree for our program. So a JavaScript program is simply a list of statements and what is a statement? Well, a statement can be a few things. So it can be an expression. What do I mean by an expression? Well, in JavaScript, we make this distinction between statements, which are like, do this, do that, then do that, and expressions, which can be compositionally used inside of each other. So you can't, like, for example, declare a var inside of an expression. And actually, let me go ahead and say var is a valid statement. But any expression is a valid statement because you can just, for example, call a function, and that works perfectly well as a single line in a JavaScript program. Actually, I lied a little. We can also initialize variables with some expression. So I'll just put that in here. It's optional, though. You don't have to do that. Another thing that's not a expression in JavaScript is if statements. This is in contrast to Haskell, where if statements were expressions and could be nested inside of expressions. You can't do that with if statements in JavaScript. You'd have to use the ternary operator in that situation. Inside of an if statement, we can have as many statements as we want. So we'll just represent that as ... And then there's an optional else statement, which says, hey, if the condition is false, maybe do some other set of statements. So that's all the statements we're really going to want to care about here. So let's take a look at what kinds of expressions we can write. So an expression is, it's a fragment of program that can be, used within itself, right? So there are a few things. So like the lambda calculus, functions in JavaScript can be anonymous. So we'll say, hey, a function can be used in an expression to define a function, to define a closure in our JavaScript program. Oddly enough, assignment is an expression, not a statement. In Python, assignments are not allowed as expressions, but JavaScript allows for you to do assignment nested inside of a deep expression. It's frowned upon. You really shouldn't do it, but it's allowed by the language standard. We can obviously call functions if we are inside an expression. So the body of the function call takes as many expressions as we want. And then, there's a bunch of things. So we can refer to a variable, so put in some identifier. We can have some numeric literal or Boolean true, or any of those like that. We'll just say literals, they're either Booleans, null, or some number. We're not going to support like floating point or anything like that. And then for extra, jazz, JavaScript supports a number of binary operators that are infix. So these are like plus, minus, and, or. The logical operators we actually have to support them specially in our interpreter, because in JavaScript they're short circuiting. In Haskell we didn't have to do anything special because Haskell was lazy, and so we wouldn't execute the second half of these logical expressions. We didn't need them, but in JavaScript you need to actually do something special in the language to get the support for these. And just to cap it off, all I need to do is say how to define a function. And so we'll just say, function, well, you write the function keyword, and then you give some name for it. Now, technically in JavaScript, you're allowed to omit the name of a function, and that just makes it an anonymous function. But if you recall in our previous notebook, we said that we were going to be okay with referring to functions as code by some name. So we're actually in the fragment of JavaScript we're going to support here, we're going to require every function have a name so that we can conveniently refer to it when we define our closures. So this identifier is not optional. And then you give your arguments to the function inside of parentheses. And then finally, we have the body of the function, which is some series of statements on the inside. And then finally, at the very end, we have some expression, which we're going to return from the function. So some more features that we're not going to support is ordinarily in JavaScript, you can put a return statement anywhere in the function body, and that will trigger a short circuit. But we're not going to allow that here. That's just that's something that you're going to add support for when we take our interpreter and generalize it to work with continuations. But for now, we're just going to do very simple Haskell style functions where you do a bunch of compute and then you return some expression at the end. Okay, so here's our syntax tree, and there will just be there will essentially be objects provided by Acorn which represent each of these things. So let me just write them down over here so that we can easily see what they are. So when we have statements, an expression is going to be called an expression statement, for example. A variable declaration is going to be called a variable declaration. Very straightforward names, what you'd expect. An if statement will just be called an if statement, and so forth. So let's skip statements for a moment. They are a little important, but they're kind of not interesting in some sense. And let's go to the expressions. So the expressions are also going to have names. They're going to have types. So expression can be a function, which will just be called a function expression. They can be a assignment, so we're going to call that assignment expression. sorry, we're going to call them, but Acorn calls them. When you do a function call, that's a call expression. When you have an identifier, that's just identifier. Literal is just literal. And a binary expression, actually, there's two different variations. So a binary expression is just one of the numeric operations. And logical expressions get their own special name. Why do they get their own special name? Well, that's because they're short circuiting, so you do need to handle them specially. Okay, so let's go ahead and define an interpreter for expressions right now. Let's just do it. So we need to think about what kind of function type we're going to do, and we're going to think about how exactly we're going to put this implementation together. So at this point, ordinarily, I would ask the class, hey, if I want to evaluate an expression, well, clearly I need to know what the expression I want to evaluate is, but what other things do I need to actually evaluate an expression? And if we think a little bit about this, we will see that there is one more piece of information we need. We need to know what the environment we're executing this expression is in, right? Because otherwise, if we have identifiers that we're going to refer to, if we don't have an environment, we won't know what their values are. So this is essentially what we talked about as the current environment pointer, right? It points to the environment that says what the lookups in the expression are supposed to do. So hey, so now we need to go ahead and actually evaluate this. And what I'm going to do is I'm going to do a switch statement on the type of the expression. That's just going to tell us which of these blue names we actually have. So if we have a function, this X type will be the string function expression, and so forth and so forth. It's kind of like pattern matching in Haskell, but not as nice. So let's do a simple one. So let's say that our expression is a literal. So when our expression is a literal, we don't have to do anything. The AST representing a literal is simply a literal, and it's some value. It's a JavaScript value representing the constant in the program at that point in time. And because we are maintaining the same representation for numbers and booleans and and nulls between both the host language, the JavaScript that we're writing our program in, as well as the internal language, the JavaScript that we're interpreting over, I can actually just reuse this value directly from the abstract syntax tree. So all I need to do is return the value that is inside the literal here. So in this situation, the meta language and the language representation is the same. But remember, this only applies for the basic primitive types. If we're talking about, say, functions, the representations are not the same, right? A function in the host language is this opaque object that you just call and then you get something. But a function in the target language, the JavaScript that we're interpreting, if we recall from our previous diagram, we're going to represent those as objects, right, with a code pointer and an environment pointer. Okay, enough about that for now. We'll get there eventually to talk about in more detail. So let's do another example. So let's do identifier. So this is the function that we've got some name, exp name to be precise. We've got an exp name which says what it's a string saying what variable we referred to in the expression here. And what do we do when we need to evaluate an expression that's just a variable? Well, we need to look it up in the environment. So we actually we already wrote the function to do this, right? We called it lookup variable value. So I don't need to implement it again. I'm just going to call that function over here and call it a day. So let's just return lookup variable value. And what do we have? Well, we've got the name of the variable that we want to return, and we've got the environment. And if it seems like I'm pulling the field names out of a hat, that's because I've got the documentation and I'm looking at it in another screen. And you can look up the documentation too, right? So for say a identifier expression, it'll say, hey, this is an object and it only has a name field. Okay, so so that's our identifier. So we've done some pretty simple things, and let's keep doing simple things. I like simple things. So the next type of expression we're going to do is a little different, but not too much different. So we're going to do assignment. So assignment, it's going to have a name, and it's going to have a expression. We'll just call this right, because it's the right-hand side of the assignment. And so for assignment, there's a little bit of trickiness. So obviously, we have already done most of the work for assignment, right? We already wrote a function which, given a environment, a variable name, and a value, sets it in the environment. So you might be tempted to write something like, hey, let's go ahead and just set variable value, and then what? We called it exp name, exp right, and env. Let me just delete this guy. Working on expression, don't forget that. And then the env, right? But there's a problem. So the problem is that exp right is an expression. It's basically saying, hey, this is the abstract syntax for how you would compute the thing that you are going to pass in. So if I wrote, for example, x equals 2, this wouldn't be a 2, but it would be a object of type literal whose value was 2. So that's no good. We don't want to do that. We need to evaluate the expression first before we actually use it. So how can we do that? Well, fortunately, we are working on exactly the function we need, eval expression. So instead of just directly using the expression, as I've done here, we're just going to evaluate it first. So I was finishing off assignment. I said I was going to evaluate the expression to give me the actual value that was returned. And there was one last thing that we need to do, which I'm not going to do here for sake of time, which is that when I have an evaluated expression, I actually need to return it from the assignment in that situation, because when I assign a value and use that as an expression, which I just told you really shouldn't do because it's not very good, very good quality JavaScript. But if you do that, you do get the value that you assign to the variable as the return value of the expression itself, right? So if I say y equals x equals 3, y will become 3 because that's what x was assigned to. So you just need to implement that correctly, and you can do that by just making sure you return the correct the value that you got from expression back in this case. Okay, so there are a bunch of other expression types, like the binary operators and things like that, but I'm not going to actually implement them here because I want to skip to the really interesting one, which is function and function calls. So let's talk about function for a sec. So function, it's pretty complicated. But we're gonna simplify things. So the way we're going to simplify things is we are going to represent functions as we're going to represent functions as code and as the environment they were allocated in. So really, when I want to return what a function expression is, there's only really two things I have to work out. I have to return what the code is, and I have to return what the environment is. And I just reminded myself that I don't actually need quotes for making records in JavaScript. Okay, so what is the code going to be? So when I have a function, I have some giant expression which says, what the name of the function is, what the parameters are, and all the statements. So I'm going to cheat, and I'm just going to store the entire expression here as the code. And we'll just figure out what to do with it when we're actually writing the code for actually calling a function. And then for the environment, well, functions just remember what environment they were allocated in. So I can just go ahead and, sorry, let me just make my dead zone clear in my screen so I don't draw past it. So if I have an environment, I'll just save it to the closure, and that's it. That's all I need to do. And so functions end up looking pretty simple. Now, to actually call a function, however, that's where we're going to have to bring in the big guns. So we're going to say, what happens if I call a function? Well, I have an expression which is the callee, and then I have all of the arguments, which are going to be called arguments. That's what I'm going to need to do. Okay, so let's take a look at calling a function. So for now, what I'm going to do is I'm going to cheat. So I'm going to assume that I have some function called apply. Remember that loop between eval and apply, right? So that's what I mean here. Apply is going to be a helper function that we use to specify how exactly we should go about executing functions. And eval is, well, it's the thing we're writing right now, which just says how to actually, go ahead evaluating expressions in the normal case. So all I need to apply something is I need the closure representing the function, and I need the arguments. Now, is the closure just the callee, and are the arguments just the arguments that are in my expression? Well, similar to what happened with assignment, where I don't pass the asterisk syntax tree, I need to pass the actual evaluated value in the runtime system. With call, I have to do something similar. I need to actually pass the result of having evaluated the expression on the left-hand side and evaluating each of the arguments. So there's a little work I have to do before I do this, right? So I have to first take my callee and evaluate it. And once again, where am I going to evaluate it? I'm still going to evaluate it in the current environment because that's just the environment I'm in. And then I need to evaluate each of the arguments, and I'll use JavaScript's handy dandy map method, define on lists, which lets me just define a higher order function, which will just go ahead and do the evaluation on each expression individually. And so really the crux of the matter is, how do you implement apply? What exactly do you do? Question mark, question mark, question mark. So let's figure that out. Okay, so I'm just going to get rid of this eval code, and we are going to work on apply now. And what did we say apply takes? Apply takes a closure, and it takes some arguments. All right. So before we start trying to write this function, let's remind ourselves a little about how exactly function application worked when we did it diagrammatically in lecture last week. So the way we we did function calls is we allocated a new environment. We added the parameters to the environment. We also added all of the variables to the environment as well. And if you recall, at the end of lecture, we talked a little bit about variable hoisting in JavaScript, which for var means that we have to go ahead and collect up all of the vars inside of our function to actually get all of the things pre-declared in the environment before we actually started executing anything. And then we went ahead and evaluated the statements inside of the function. So we're going to do something very similar when we write the code for this. But there's a few helpers that we're going to sort of assume that we've written already, and then we'll have to write out the implementations for those helpers. So I said I was going to pack up the entirety of the function here. And so let me just tell you a little bit about what is going on inside of this function thing. So when we defined a closure, we said we were just going to package up the entirety of this function as the representation of the function in question. And so that's the expression. So we had some expression. It represented a function object, and the code field of that function object has all of this stuff. And in particular, the list of parameters is a subfield called params. And the statements themselves are going to be the body of the function in question. And well, that's it. That's most of all we need. But remember, the closure itself is not just the code, but it's also an environment, right? So the closure is an object with a code pointer and an environment pointer. All right, so let's get to it. So we are going to, let's just assign out the code and the env just to make it a little easier to handle. And what are we going to do? So we need to allocate the new environment, right? So let's see how we can go about doing that. So we're going to call this new env. We need some way to basically extend this environment. So let's imagine that we have some helper function extend environment. And what exactly is this helper function going to do? Well, a bunch of things, right? So it needs to take in all the parameters of the function in question. So, this is going to be the code and the params field. In the real lab, it's a little annoying. The parameters are identifiers, so you have to map out the names from them to get string names. Otherwise, they're these identifier syntax objects. Okay, so we need the parameters because we're going to add new fields in the environment for each of the parameters. We also need to assign the values to these parameters, right? Because the parameters don't get initialized as undefined. They get initialized with whatever it is I pass to the function. Fortunately, I have all the arguments that I'm passing to this function, so I can just go ahead and pass those along. I also need to make fields for all the var declarations in here. Now in the lab, there is a helper function that I'm not going to implement here called hoist. And what this does is it will take all of the, it will look through all the statements here, looking for variables, let me just do this exactly the code you're going to write. It's code.body.body for hysterical reasons. It will go and scan through all of the statements looking for var declarations and then return a list of, A, B, C if there was var A, var B, var C inside the function. An extended environment is just going to create undefined entries for each of these. And finally, there's one last thing we need to do, which is that when we create a new environment, we need to say what the parent environment is going to be. And the parent environment, what is it going to be? Question. If there's a real lecture, I could ask y'all what should go here, right? So you don't want to put env here, and quite savvily, we have not actually taken env as an argument to apply. We want to pass in the env from the closure. All right. So this gives us our new environment. So we have a new environment. We've got a bunch of statements that we want to evaluate. So really all we have to do is evaluate the statements. I didn't tell you how to implement this, but hopefully it's not too hard to see how you would go about writing eval statements. So we'll need to pass in the body because that's how the syntax tree goes, and the new env, not the old env, right? Because if it's the old env, then we won't have any of the parameters in scope. And that's apply. So of course I've elided the sort of most important function here, which is how to actually extend the environment. But really this is, not that big a deal. We just need to, go and faff about in JavaScript setting it up. But let's go ahead and implement it for right here, right now. So function, extend, environment. And what are we going to do? Well, we've got the parameters. We've got the value args that we passed for them. We've got the hoisted IDs, let's call them HIDs, and the environment that it's going to be the parent pointer. Okay, so we need to return some new env. Let's call it new env. And I'll start off by just, setting up what the parent pointer is going to point to. Oops, I don't need the parentheses. It's going to point to the, env that I passed in as an argument. And then I just need to go through each of the parameters and each of the hoisted IDs and make entries in my environment for each of them. So, hey, for I equals 0, blah, 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 while I is less than params length, and increment I every time through the loop, let's just go and in my new environment, assign the string parameter name with the argument value that I was invoked with. And then of course for each of the hoisted IDs, I is less than HID's length, I plus plus, let frame new env HID's I equals undefined. And there we go. There's a little bug in this code, and the little bug in this code is that what should happen if a var statement and a parameter collide. So if I have like function x var x equals 2, do I just lose the argument that I got passed in for x? And the answer is no, you don't, right? So if I refer to x in before the var declaration, I should see whatever it was at the parameter. So I actually messed up. I need to set up my hoisted IDs before I actually set them up for the actual parameters. So oopsies, just goes to show that I can make mistakes too. Okay, so that's apply. We've got all the pieces. So let's just talk about where we've gone in this lecture. So we wrote an eval function, right? We said, given an expression, how do you evaluate it? And all that function did was it looked at what kind of syntax you had for the expression in question, and it wrote a little bit of code to do the evaluation. And in most of the cases, things were relatively simple. What was not simple was when we wanted to call an expression, right? To call an expression, we had to do some work. We had to allocate a new environment, and then we had to start evaluating inside that new environment. So we wrote a helper function for that case called apply, which says how to apply a number of arguments to a closure. But hopefully what you can see from all of the stuff that we've done here is it's actually not that complicated. We have written a JavaScript interpreter with a few pages of code, and it'll work. So when you do this in your lab, you will be given an actual honest-to-goodness working JavaScript interpreter. And there's a bunch of ECMAScript compliance tests, which I've included in the lab to help you with testing. And you will find that if you've done it all correctly, all your tests will pass. So you will have actual honest-to-goodness JavaScript programs. And even cooler than that is because you have all of this interpreter code in front of you, you can actually go and, for example, change the behavior of your JavaScript interpreter to do interesting and wacky things that you wouldn't normally easily be able to do if you were just working in JavaScript directly. Now, there is a little, let me see. I do feel a little bad with just this here because this is the simple treatment where we've just gone ahead and done the same thing that you could like have opened up SICB and done. But later, we're going to talk about control flow. We're going to talk about continuations. And then the follow-up lab from this, which you can take a peek at if you're curious at, the follow-up lab is going to involve, we're going to take this interpreter and turn it into continuation passing style so that we can implement control flow. Because as you may have noticed, we have not implemented any sort of non-trivial control flow besides if statements, which it'll turn out are very easy to implement. You just do an if statement. And in the meta language, and the if statement in the meta language is good enough to give you the if statement in the inner language, but that won't necessarily always be true. All right, so that's all the topics I wanted to cover for today. And sorry about not being able to give this lecture live. And if you've got any questions, any thoughts that came up during the lecture, please send them my way on the forums or email, and I would love to answer them because I didn't have a chance to answer them for you today. All right, thanks everyone, and see you on Wednesday.